Today, we are diving into a question that gets right to the heart of, well, everything. It's this incredible paradox that pits the beautiful, organized complexity of life against the most fundamental laws of the entire universe. Let's get into it.
So here's the problem, right? The universe has this one unstoppable rule. Everything trends towards chaos, towards disorder. But then you look around and you see life. You, me, every plant, every single cell, we are all masterpieces of unbelievably intricate order. So how? How is that even possible? How can all this amazing order come from a set of rules that seems to demand the complete opposite?
And look, this is not some abstract philosophical thing. Your own body is doing this right now. You take in food, that's just chemical energy, and you use it to build and maintain this incredibly ordered system that is you, all while releasing heat and waste into the environment. We are literally living, breathing examples of this cosmic puzzle. To solve this, we've got to understand the rules of the game. And these aren't just any rules. Albert Einstein himself said that the laws of thermodynamics are about as fundamental as physics gets. He was totally convinced they would never, ever be proven wrong. So this is key. Life doesn't get a pass. It can't break these laws. It has to work with them.
All right, so let's start with the basics. If we're going to figure out how life pulls off this amazing trick, we first need to get a handle on the language of thermodynamics.
First up, a couple of key terms. When scientists talk about energy, they like to split the universe into two parts. You've got the system, that's the specific thing they're looking at, like a reaction happening in a beaker. And then you have the surroundings, which is, literally everything else. It sounds simple, but this distinction is absolutely crucial. Okay, so these systems are defined by how they talk to the outside world. An open system, think of a pot of boiling water, can swap both energy and matter. A closed system, like a sealed water bottle, can swap energy, it can cool down or heat up, but no matter gets in or out. And then you have an isolated system, like a perfect thermos that doesn't really exist, which exchanges nothing at all. So here it is, the big reveal. Well, part one anyway. We are open systems. We're constantly taking in matter and energy by eating, drinking, breathing, and we're constantly releasing matter and energy back out. This one fact, right here, is the key that's going to unlock this entire paradox. Don't forget it. Now, the rules themselves are the 4 laws of thermodynamics. The first and second came about in the mid-1800s. The third showed up in the early 1900s. And here's a fun little bit of trivia. The zeroth law was actually named last. Why? Because scientists realized they needed a more basic rule to come before the first law, one that just establishes what temperature even is. First up is the first law, and you probably know this one. Energy is conserved. It's beautiful and simple. The total amount of energy in the universe is constant. You can't make it, you can't destroy it, you can only change its form, like from the chemical energy in your lunch to the kinetic energy of you walking around. Yeah, you can think of it like this. The universe's energy books always have to balance. Whatever energy you start with, that's exactly how much you end up with, just maybe in a different column on the spreadsheet. The totals always match. Okay, so if energy is just conserved, what's the big deal? Well, the first law doesn't tell us anything about which direction things go. For that, we need to talk about probably the most famous and most misunderstood concept in all of physics, entropy. The second law says that the total entropy, which is just a fancy word for disorder or randomness, of the entire universe is always going up. Every single time energy moves or changes form, some of it just kind of spreads out and becomes less useful, usually as waste heat. It's the universe's great one-way street, always heading towards more randomness. And this is what we mean by disorder. Imagine a perfect crystal at the coldest possible temperature, absolute zero. Everything is perfectly ordered, so it has zero entropy. But the second you add heat, those molecules start vibrating and bouncing around more and more randomly. That increase in molecular chaos is the increase in entropy. This law is exactly why your hot coffee gets cold. The concentrated heat in that little cup spreads out into the bigger, colder room, and the overall disorder of the room plus coffee system goes up. The reverse, all the random bits of heat in the room suddenly deciding to jump into your cup, well, that's so ridiculously improbable that it just never ever happens. The law says total chaos has to increase. Okay, so now we have our paradox in full view. The universe demands chaos, but life creates order. The solution comes from this brilliant piece of science that gives us a way to figure out how much energy is actually available to do useful stuff, like build a cell. So let's ask our question again, but with what we know now. If every single thing that happens must increase the total entropy of the universe,
How in the world can our bodies do things that decrease entropy locally? Like taking a bunch of simple, messy amino acids and building them into a complex, perfectly ordered protein? The answer is right here, in this powerful little equation from Josiah Willard Gibbs. Now, I know equations can look a little scary, but this one is amazing because it connects the first two laws. Okay, let's break it down. This first part, delta H, is the total heat or energy change in a reaction. That's our first law. This second part, T delta S, is the energy that becomes unusable because of disorder. T is temperature, and delta S is the change in entropy, our chaos from the second law. So what we're doing is subtracting the energy taxed by chaos from the total energy change.
And what's left over, that delta G, is called Gibbs Free Energy. You can think of it as the net profit of energy from a reaction. It's the actual usable energy that's left over to do real work, like power a muscle or build a strand of DNA, after entropy takes its cut. It's the energy that's free to do something useful.
And here is the truly elegant part. The sign of that delta G tells you everything you need to know. If delta G is negative, the reaction will happen all by itself. It's spontaneous, and it releases free energy. We call those exergonic. But if delta G is positive, that reaction is not going to happen on its own. It needs an energy payment to get going. We call those endergonic. And if it's zero, well, nothing's happening. The system's at equilibrium.
All right, let's bring it all home. We have the paradox, we've got the laws of the universe, and now we have our secret weapon, Gibbs Free Energy. Now we can finally see exactly how life manages its energy budget to create all that beautiful order.
So life is basically this constant dance between these two kinds of reactions. On one side, you have the exergonic reactions, the ones that release energy, like breaking down the food you ate. The big one in our cells is breaking down a molecule called ATP. On the other side, you have all the stuff life needs to do, building proteins, making your muscles contract, and those are all endergonic. They cost energy.
So how does life solve this? It's a clever trick called energy coupling. Your body is incredibly efficient. It performs an exergonic reaction. It breaks an ATP molecule that releases a nice little burst of free energy. And then it immediately uses that burst of energy to pay for an endergonic reaction that needs to happen right next to it. It's like using the cash you get from one sale to immediately pay for a purchase you need to make.
And that brings us to the grand finale, the answer to our paradox. Life does not break the second law of thermodynamics, not even a little bit. It builds and maintains its incredible internal order by exporting disorder to its surroundings, by burning fuel, by releasing heat into the air, by breathing out carbon dioxide. We, as open systems, are constantly and massively increasing the entropy of our environment. So the total entropy of the universe still goes up, just like the law says it has to.
So you see, life isn't some weird loophole in the laws of physics. It's their most elegant and complex expression. It's this beautiful little island of order that exists by paying a chaos tax to the rest of the universe. And it kind of makes you wonder, what other fundamental rules of the universe are we, just by being alive, the most perfect examples of?